edit, at least the beginning. See, if that stuff was written in Haskell, we would never have lost those 12 minutes of our life. All right, so this is the Haskell class. It's all honor system. You know, there will be exercises, do as much or as little getting graded. I'm the one who gets a grade, because if you understand Haskell and you feel comfortable with it, then I've passed. 5, 10, 15 people feeling comfortable enough with it to use it professionally here. And obviously, if me down, I think I've set a reasonable pace for this class, but you know, I'm not always aware of what is new and what is unclear, so slow me down. My experience is that if there's one person who is struggling with something, there are at least 3 others who are struggling too, and that means that I need to explain what's going on. All right, so here's the syllabus, at least as it looks now. This first class is going to be why Haskell, functional programming, and the interactive mode, which is called GHCi. The second lecture is going to be user-defined types, specifically algebraic data types, which is the model of all types in Haskell, or almost all types. The third is on July 6th. We're going to do a lab where we take some code, we're going to dissect it, then there will be some exercises where you can, if you want, go off and improve it. I recommend looking at the code before the lab. I'll send out an email probably on Wednesday or Thursday. The game's called Dodgy Dice. Not super interesting game, but it'll get you used to looking at Haskell code. The third lecture, July 8th, is going to be anonymous functions or lambdas, get into some of the details of types, and then we're going to tackle laziness. Laziness is the feature that gives Haskell the reputation for being really hard. And laziness isn't that hard. It has a certain set of rules that are different from what most languages present. But once you learn the rules, it's quite accessible. And if you want to turn the laziness off in Haskell, there are ways of doing that. On the 13th, we'll go into the prelude, which is sort of the core functionality that is implicitly loaded into your GHCi, or in Ruby you would call it IRB. In Clojure it's the REPL. The 15th we will be doing type classes, and that is that's sort of where Haskell starts to shine. The second lab, we're going to deal with some file I/O. We're going to do some parsing for a Lispy S expression language. Those of you who were in my sales pitch on Friday saw that. Hopefully the remaining bugs will be worked out. And then lecture 6 is going to be some of the more interesting type classes, functor, applicative, and the dreaded monad, or the dreaded M word, which is monad. Now, once we've tackled monad, and realistically, it's probably going to take a couple more lectures to show how all these ideas fit together, the language really opens up to us. I think of type classes and the monad concept as like the airship in a console RPG. You know, you've got this linear plot, you fight this boss, you collect that item, you fight that boss, and then you get the airship and the world just opens up. And there are all kinds of crazy side quests, like, you know, you can free the monads, or you can fight the dragon down there, or collect the golden lambda. So the dreaded monad is just the first hard boss. That's why people complain about it and say, oh my god, monad, it's, you know, it's so hard. It's not really that hard, it's just a type class. It's only hard because you have to learn type classes, you have to learn a little bit about higher kind of types, but I'm going to be teaching all that, so not to worry. Once we've done that, once we've gone through the basics, so actually the week of the 27th I'll be out, the last week of July, but I come back in August and there's a lot of stuff we can do. We probably want to do Haskell in the large, building a Cabal project, multiple modules interacting with each other, you know, just the nuts and bolts of that. Haskell in the web, We have multiple web frameworks in Haskell. I'll probably be using one of the simpler ones. Some of them are very complex. There's one called Yesod, which there's a whole book on it. I'll probably just be using Scotty. We'll talk about the lens library. That takes the one good thing that object-oriented programming has and implements it in Haskell, which is a certain syntax for updating nested data structures. I'm sure that sounds riveting. After that, concurrency, parallelism, and distributed computation. And this is not necessarily the order I plan on taking. These are just some ideas that I have right now for future topics. But generative testing is really neat. There's a library called QuickCheck where you assert properties about your code, but QuickCheck itself will come up with test cases, and it'll try to find counterexamples, and it's probably better at that than you or I am. And finally, high performance computing, vectors, unbox types, GPU acceleration, a lot of things that you can't really do in, or that you typically think that you can't do in a high level language, you can do in Haskell. In fact, with GPU acceleration, you're doing things that are hard to do even in Java. So to get started, you want to install the Haskell platform. That's probably the simplest way to get going. You'll get GHC, which is the compiler, GHCi, which is our REPL, and Cabal, the package manager. So does everyone have GHCi?
I don't.
You don't?
I don't either.
Okay. So what I want you to do is Google the Haskell platform.
If you're on a Mac, you can actually do brew install Haskell platform, and then also Cabal. Brew install GHC and then Cabal -install.
Okay, whichever one you want, and it's not super important in the short term. But this
I'm just
is an
sending that out
interactive
to the
class,
chat.
so-
I don't have Wi-Fi. So.
Oh, you don't have Wi-Fi. Okay, you can, if you want, you can come around. Oh wait, I can't let you use my machine because I'm using it to present. Okay, I mean. Okay. So yeah, I mean, in general, I prefer for this class to be interactive. This first one you can certainly go through without having a REPL set up. Okay, so should I continue on?
Thanks.
Okay, so some advice and some hints. You want to do a lot of exploring in this language, so start with GHCi. Just every time I say a function has a type, try to prove me wrong. Try to use that function. Maybe not while you're in the class, but certainly when you're working through the slides, it just helps to, if you look for errors in my slides, hopefully you won't find any. That's a good way, at least for me, to learn. You learn that something is true by trying to prove it false, unless it actually is false. If I lose you, slow me down. I recommend reading the slides after class again, because I'm going at a reasonably aggressive pace. And finally, you're going to see a lot of type signatures, because that's what makes Haskell what it is the static typing. And when you start out, they're kind of hard to understand. Like this guy, you add 3 to the string dog. Now that's obviously nonsense, unless you're a Java programmer, in which case it's 3 dog. But that type signature, doesn't look like what you would expect. Rather than saying you can't add a number to a dog, it's saying instance for num char in brackets. You'll understand that by lecture 4 or 5. Just don't worry about it for now. All right, so using GHCi, and those of you who have it up can see this. Up top, we're using it as a calculator. First thing you do with a REPL, 27 plus 42, 69. The double equals on the second item is the comparison operator, one of them. We have the :T for true. That's how you get a type. Or you can spell out :type, but I usually just use :T. That's something that you can do at the GHCi, at the REPL. The fourth, let x equal 100, we're assigning 100 to the variable x, and then x plus 37 is 137. These are some function definitions at GHCi. We're letting f of x equal x plus 7, and we get a unary function. And then we're letting g x, y, z be x plus y times z, and we get a 3-argument function. By the way, does everyone here know what arity means? Okay, so arity is
How do you spell it?
A-R-I-T-Y. It's the number of arguments that a function takes. It's just, it's a mathy term that we use for the number of arguments.
So the arity of the first thing of the one, the arity of the second.
Exactly. Exactly. You'll also hear the word null arity, which means zero arity, but we don't have zero arity functions in Haskell. And then you'll hear unary, which is arity 1, binary is arity 2, ternary is arity 3. We have let expressions in Haskell. In GHCi, there are actually two meanings of the let statement. The first is assignment, and that is global to the GHCi session. So you do let x equal 23, and x is going to be 23. The other is local assignment. And this is one of the things I don't like about GHCi is that they mean totally different things. The let is a global assignment. The let inform on the bottom is local assignment. So you're having y equal x plus 100. X refers to the global to GHCi 23, and y becomes 123. But then that y is thrown away because it's a local variable. So for an exercise, let's try to predict the outputs of this. And if there's disagreement, we can have a fun little debate. What do you guys think is going to return to the console when we let w equal 4? Do you think it's going to be a type signature?
Yeah.
Like in Scala? Okay. What do you think?
Nothing.
Nothing. So you're actually right. It just doesn't return anything. It's assigning 4 to that local or to GHCi global variable. What do you guys think this is going to return? 10. Anyone disagree with 10? It's the right answer. Because the 4 plus 6. What do you guys think this is going to return?
29.
Does anyone?
Oh, dummy. Yeah.
Oh,
Failure?
No, it's going to return 27.
Okay, so we have 27. We have failure. What do you guys think? 27. Okay. Does anyone not think 27 or not know why people think 27?
not the case, and nothing.
No, just I was had it back into the left.
It's 27. The local x is 23, and the w is the GHCi global 4. What do you guys think this is going to be?
Here.
An exception.
Exactly. Does anyone not think it's going to fail? Well, I already said that.
Not out.
Yeah. Because the x is not in scope. What do you guys think this one's going to be? Anyone not think 21?
I'll say 5 just to be different.
Well, then you'll be wrong because it's 21. And in case it was not clear why, the local scope, it always takes the more local scope for the variable. So that x equals 5 is shadowed. It's basically not visible in the scope, in the inner scope. The compiler will be nice enough to warn you if you make this mistake in compiled code. So that said, let's talk about what functional programming is. And the core idea is that a function should have stateful effects as rarely as possible. This factorial is int to int. That's a type signature. We don't know from that whether factorial is right, but we know that it doesn't write to disk. We know that it doesn't use random numbers because that is actually updating some state somewhere. We know that it doesn't check the system clock, and we know that it doesn't launch missiles or blow our hand off. But this weird factorial, which is int arrow IO int, all bets are off. Because what that means is that weird factorial takes an integer and it returns an action that returns an integer. And that action could do things. It could, check the RNG. I mean, it wouldn't be implementing factorial then, but it could do that. You're going to see this lambda notation a lot. It's the Greek letter lambda. It represents the concept of a function as a first-class object. So you see lambda x dot x plus 1. That is a function that takes an x and it returns x plus 1. Yes?
In regards to the IO that you were talking about a minute ago, what a function returns doesn't necessarily, in the classical sense, dictate what it does like during its own operation. So is there something specifically in Haskell that inhibits you from using IO unless you return an IO, or could you have just in the beginning there accessed IO to get the use the clock to randomize something, or does it stop you?
Okay, that's a great question. So let me think about how to say that intelligently so I don't make it more confusing. So the main, which is what's actually getting executed, has type signature IO of unit, where unit is a type. It carries no information. Now, the way that you build up to your main is by composing larger and larger functions. Your stateless functions will not have IO in them, hopefully. But once you have an IO, there's no way to get, actually let me back up a little bit. There's no way to get from an IO of A to an A. Like there's no IOA arrow A function. Except there's a thing called unsafe perform IO, which does exactly that. It lets you subvert the type system, and you should probably avoid using it whenever possible. It's there for people. It's there as a way of changing the type signature of something that you know is safe, but that the compiler doesn't know. But that's a really advanced topic, and yeah, we probably will never encounter unsafe perform IO in this class.
Maybe like a follow-up question, like what if somebody gave a type signature that didn't have an IO, but then performed an IO operation within the body?
That is,
anyway, like basically they promised they wouldn't do it, but then they went ahead and did it.
unless they use unsafe perform IO, that's impossible. Or there are other unsafe functions, like there's an unsafe coerce, but that would not happen. Although there is one issue around exceptions. I will discuss this at length later on, but in general, throwing exceptions from non-IO code is bad form, although plenty of standard library functions do it for historical reasons. So there are edge cases, but in general, coding using normal practices, you won't go from an IO to something that's not an IO. And using normal practices, something that is in arrow int will not be doing IO. So these are definitions of this lambda expression in different languages. We have a C function or a Java method. We have a Ruby method. We have a closure function. And we have the Haskell version. When you see minus minus in Haskell, that's a comment. And you can either define add 1 x equals x plus 1, or you can define just add 1 equals, and then the lambda expression, lambda x to x plus 1. In Haskell, you use an arrow rather than a dot, as you would in pure lambda calculus. So the concept of first-class functions is core. You can pass a function into another function. So does anyone have a guess as to what this returns?
Return the square of each element, right?
Exactly. Does anyone disagree? This is a function that exists in pretty much every functional language called map. If you haven't seen it, that's fine. You will see plenty of it in this class. Map takes a function and then a list, and it applies that function to every element of the list. So it's going to return 149 in this case. You can also return a function from a function, and that's called currying, and we're going to see that a little bit later on. Now, functional programming isn't just about first-class functions, because every language has some kind of first-class function these days. Even with C, you have function pointers. It's about making it easier to reason about code. And there's this misconception out there that functional programmers don't like computational state. We don't like quote-unquote side effects. And that's really not true. We don't like unexpected stateful effects. State is fine. Our program's job is to manipulate the state of the world. We just want to know where the state is so we know what's happening to the world. Now, reasoning about arbitrary code is formally impossible. Gödel proved that there are statements that are neither provable nor refutable. And then 5 years later, Turing proved that there's no program that will tell you if an arbitrary program halts. Alonzo Church then proved that you can't tell if two arbitrary programs do the same thing. You can have two programs that do the same thing, but it's impossible to prove that that is true. And then Rice's theorem just said, yeah, you pretty much can't know anything about an arbitrary program. But the good news is that that's arbitrary code. And with functional programming and strong typing, what we're trying to do is make our code a little bit less arbitrary. Because humans don't set out to write arbitrary code. We don't, want to generate a random working assembly program and see what happens. We have a problem we want to solve, and we stick to this low entropy subspace of all the code that's out there. The bad news is that corporate code usually falls to pieces over the years. Usually it's not one programmer who's responsible. It happens when you have 7 or 8 or 9 maintainers over 30 years. You get the too many cooks problem. Or, this agile / scrotum stuff, generates a lot of unreasonable deadlines, and people throw a bunch of crap in to get their user story points or whatever they call that shit. So anyway, two of the core virtues of functional programming are referential transparency and composability. Referential transparency means that something returns the same output given the same input every time. And composability is the ability to put things together and not have, grossly unexpected interactions. Now, how many of you have heard that functional programming is slow? Who's heard that? You don't have to believe it, just have you heard it? Okay, so we've heard a couple people have heard that, and I have. And it's not really true. Obviously, the machine itself is imperative. It's, updating registers and all that. But the fact just is that imperative code has had a lot more optimization put into it than functional code. But there are also a lot of optimizations that are available if you know that code doesn't have hidden state. So for example, we're going to go over one just very small optimization. You've probably seen this, XKCD. And I want to ask the question, is this optimization legitimate? Most people are nodding. Does anyone think it's not? Okay, great. Because we're doing half the work because factorial of 100 never changes. So this is completely okay. How about this guy? Is this legitimate? No. Heard a no. Anyone think it is? Why is it not legitimate?
You're only calling
Well,
random
because-
ones.
Function random, given no argument, doesn't ever return, it's not supposed to return necessarily the same thing.
Exactly.
When called twice, but on the right side, it's saying X is the result of it being called once. So you're always going to get it twice when you called the first time.
Exactly. You get a different distribution because here on the right you're only calling it once. And this is not Haskell. This is some pseudo code language because you can think of it as say OCaml type syntax where random is a function that takes a unit and returns a float. That optimization is not okay. Now composability. Function composition is a lot easier to reason about than the composition of stateful effects. So let's say that our computation is this guy, h of f of x and a g of x. The question is, can you legally parallelize it? What do you guys think?
It's unknowable right now. What I would say.
That's just immutable.
Yes, because they don't depend on each other.
Okay. So the answer is, Gabe got it. It's if they're stateless, then yes, you absolutely can. You can farm f off to one machine or one CPU and g off to another. But if x is some mutable structure, then the answer is no. And so for an example, we have an int ref. This is, again, some pseudo language I made up, but it's like an integer in Java. We initialize it to 0. And we have these f and g that sleep for some amount of time, and then they take this int ref, they in-place update it, and then they return what's in it. So what is h of f of c, g of c in a single-threaded world? Why do you say 11?
Because of the. Oh, wait a minute. I didn't see. I wasn't looking at H.
Because g is going to return 11, you're thinking, right?
Well, in a single-threaded world,
In a single threaded world, those sleeps are gonna
it's going to be 12.
order.
Well, yeah, because they're references, right? They're not. It's a pointer because
It's 12 or 21. I didn't specify the order. If it's left first evaluation where f happens before g, then you get 12, as you can see there. Because f happens, it updates the cell to 1, returns 1. G adds 10 and puts 11 in the cell, and it returns 11, and h returns 12. But if it's right first, then you get 21. And many languages are right first in their evaluation. So it depends on the language specification. But at least there, you can actually look it up, and if you know the language, you know the answer. What do you guys think this h is if f and g are evaluated in parallel?
same as 11, right?
2.
So the answer is it can be a lot of different things. It's called a race condition, and it's really bad. We have g starting, and then some kind of external event takes 6 milliseconds of wall clock time. And remember that sleep, the contract of sleep is that it'll sleep at least that long, not exactly that long. And the other thing is that this plus equal operator may or may not be atomic. If it's not atomic, we could have f and g waking at about the same time, both read 0, and then g writes back a 10, and f writes back a 1, and you get a return of 11, and the state of your cell is something you completely didn't expect. And these things are intermittent. They're called Heisenbugs, and they're really bad. So we have no idea. So it's just not safe to parallelize that unless you're like locking the int ref, which has its own set of problems. Now Haskell gives you tools to manage state. The type signature is going to tell you if a function has it, and that's great. You're going to see an IO if it has access to the general state. That means it can do whatever the computer can do. There's ST, probably around lecture 8 or 9. We'll get into that. That's a single-threaded version of the IO monad. And then we have software transactional memory. That'll be somewhere in the second half of the course. But before we can get there, we got to talk about the base types. But whenever you see a cat, that usually means a break, because everyone's got about 25 minutes of attention span. Let's take a 2-minute break and reconvene at 6:46. Unless you guys have questions. By the way, this is actually just a 2-minute break, so people think they got like 10 minutes, then they're going to come back. And
Yeah, so look at the
is everyone vanishing? Have I really lost this many people?
Yeah, so what hard security is trying to launch. Basically, I looked
Oh.
at, like,
Oh,
looking at the codes, right? I realized that document is a string, but the version in that.
my cat looks totally insane in that picture.
Cat,
Right.
probably pretty insane.
That's true, they kind of are.
Yeah, it's not great. We can't commit to it. We can write it correctly, and it'll
I didn't intend for people to leave. I intended for people to get their attention span back.
A lot of people are probably going to come back.
I think that was a bad idea.
Sure. Yeah.
We're start again.
Go ahead, sorry.
All right, so the base types are sort of the lowest level types of data. Bool has just 2 values. It's got a true and a false. Not much to that one. Int is a machine-dependent fixed-size integer. On a modern machine, it's going to be 64 bits, but you shouldn't count on it. If you are counting on a 64-bit integer, or if you are doing number theory where you can't afford overflow, you should use integer, which is arbitrary size. We also have a char.
Different than integer?
Yes, yes. Int is the 64-bit, or it's a machine size word, and it's signed. Integer will never overflow. Char is a Unicode code point. Double is a 64-bit floating point number. And then word 8 is an unsigned byte. You'll see that a fair amount. There's also word 16, 32, 64, but you probably won't see those very often. If you look at the types of the base types, they're exactly what you expect. :t true gives you bool, and on the character 5, you get char. You can commit to a specific type. And the reason you might want to do that is, for example, 5, the literal 5. It's a number, but the compiler isn't going to know that it's an int unless you tell it that it's an int somewhere in your code. Usually you don't have to explicitly type things. And in fact, you can get away with not doing it in this case. If you type 5 as an integer, you get an int. If you leave it untyped at GHCi, then you see num a, fat arrow a. That fat arrow is not the same thing as the arrow that you see in a function type. That's saying that if a is of the class num, then 5 inhabits that A. So it's saying I've got some kind of number type and I don't know what it is. And we'll get back to that later. Now, you may be used to thinking of a type as a set of values, but it's actually something that lives at the language level and at compile time. And it's an assertion about a term. It's an assertion about what type of value the term reduces to if it reduces to a value, because some terms actually just diverge forever. And it should be statically computable. So for example, what do you guys think the type of this is? And more importantly, how long do you think it's going to take to compute that type? So it's a char. And okay. Well, I would actually say that it can tell immediately that it's a char. Assuming that the expensive computation is a bool, then it doesn't have to run that expensive computation to know that it's type char, because both branches are char. So that's something it knows statically. So what's the type of this guy?
Sure.
Okay, everyone who said char is wrong. It's ill-typed because the compiler, yes, this term reduces to a well-typed value. It reduces to a char. But that's not something you can know statically. You have to actually run that computation of the 2 less than 3. And in the case that I gave, it's trivial. But in general, it may not be. So you can see for yourself, up top, we have this. It's not even an expensive computation. It'll actually throw an error. You do if error nuclear but fail, then y else n, and it'll type it as char without even running that computation. But the one that looks very simple, that we think, oh yeah, that's a char because we know how it reduces, well, it's still ill-typed, and the compiler is going to reject it. And this is formally what that looks like. You can formally reason about the code, where you say, if x bar 0 is a bool, x bar 1 and x bar 2 are A, then the if then else of those 3 expressions is also an A. That's what formal semantics looks like. Now, this is designed as a practical class, so we're not going to be doing a lot of formal or theoretical work. So if this is like gibberish to you, that's fine. It's just cool that you can, that the language does have formal semantics, whereas certain languages do not.
I'm sorry, I didn't catch that.
Yeah.
Oh, Scala's type system,
No,
Tony's.
as of 2012, did not have formal semantics. That may have changed. My knowledge may be stale. So in Python or in Ruby, function is a single type. But in Haskell, there isn't a function type. There are function types. So for every A and B, there's A arrow B, which is the function that takes A's and returns B's. So here are just some examples. They're chur and ord. Those names are like 50 years old, for converting integers to characters and characters to integers, using the code point stuff. That's not too interesting, but I just wanted to show some error types up there. And here's another one. And I put an int type on that one just because I didn't want the type classes to pop up in this example. We have a function inc, takes an int, and it returns an int, specifically one more than that. And then we have add, which is the plus, but restricted to ints. And we get this type signature. And the first thing that comes to mind there is that that looks like a function that returns another function. Does that make any sense? Is that a good way to think of add?
Add would return whatever the return value plus was. Or add.
So you're thinking add might be something that takes a tuple, a pair of ints, and returns an int.
Well, no, I mean, add would be whatever the return value of the function plus, which takes two things and returns something.
Okay.
You would know the return value of add, which is in.
Yeah.
But it wouldn't be a function that returns a row.
So do you believe me that this is the correct type signature? You do. Why do you believe me?
It's clarified.
Okay, so yes, it's currying. My wife is telling me that our dinner people are late. Okay. That's probably for the better because I'm late. So I'll explain this guy. So every multi-arity function, 2 or 3 or 4 arity, is represented as a one-argument function or a unary function that returns another function. So when you see A arrow, B arrow, C, it's just shorthand for A arrow quantity, B arrow, C. And we can omit the parentheses because Haskell will group these successive arrows from the right, like so. So we call it right associative. So if you gave add the explicitly right associative type signature near the bottom, it would mean the same thing. And in fact, you can speak meaningfully about add 1, which is not an int. It's an int arrow int. It's a function that takes the next int and it returns 1 plus that. And add 1, 2, which is quite familiar, that's just adding 1 and 2, can also be parsed as the quantity add 1, which remember is that function that adds 1 applied to 2, which is 3. And by the way, these are not easy concepts, so if you're not getting it, please review the slides, come ask me. I'm available. It takes a while to sink in. It certainly did for me. So the next thing to talk about is associativity of function application. F, X, Y, Z. How do you think the compiler parses that? Do you think it parses it from the left or from the right?
Right.
Why?
Because
I'll say left.
second, because the rest of the arguments are. Or wait.
Because you just said it was right associative?
Because currying works from left to right.
Well, okay, so the function, the arrow operator is right associative. But this is function application. So when you're applying F to X, Y, Z, what happens first? What's done to X?
It's hard to explain. I have like a bunch of functions that I wrote down.
Okay,
So the fx represents a function that takes in another parameter y, right?
yeah.
So it gets evaluated as a function which takes further parameters.
Which takes Z, right? So you're saying the one on the left.
I'm saying the one on the left, yeah.
Okay. So who thinks it's the one on the left? Okay. Who thinks it's the one on the right? And who's just like, no idea. That's fine.
Is there a fourth option?
No, it's the one on the left.
What would y of z mean?
It's the one on the left. And if you look at the right-hand side, I have right-hand sign, I don't know why, that would actually demand that x and y be functions, which they might not be. Because f is this 3-arity function that we have, but x and y and z are not necessarily functions. The form on the left we know will be well-typed. The form on the right may or may not. It is if x and y are functions, but it's probably not if x, y, and z are all integers. Yeah?
You said a minute ago that every function every multi-arity function in Haskell can be represented as single argument functions, right?
Sure.
But that would imply like some care in how you use the arguments inside of the function, right? So like for instance, if you do like f x y z is x plus y plus z, then you can say f1 and it'll return a function, right? But
Sure.
if for instance, if I just said like here, I did let f x y z equal y plus or like z plus y plus x, it's gonna yell at me if I only give it a single argument. Maybe I'll do that wrong.
No, it won't. It won't because what you're doing is you're defining. Well, let me actually show you. Let me show you an example with add, and hopefully this will make sense. So this is add, and it's a function that takes an int, which we're calling x, and it returns an int arrow int, which is lambda y to x plus y. Now, when you define that function f that you were talking about, Zach, that creates a lambda abstraction. So it's lambda x, y, z, which of course is nested. It's 3 nested lambda abstractions. And that's okay. That like the z plus y plus x, that's okay because you apply it to an x, and we'll take this offline.
Yeah, I understand
But I
the
will-
lambda calculus part. I realized that when it was giving me an error, it was actually because it doesn't know how to print an A0 to an A0 to an A0, not because it didn't know how to figure out what it was.
Okay.
So,
Okay.
my bad.
Let me explain that because a lot of you are going to run into that. That's because function types don't have an instance of what's called show. Show is the toString type class, which means that at GHCi, it can't print them. So that's what you're running into, and I'll just say there's no show instance. That's a different thing. So this is a walkthrough of currying. And if you don't understand it now, just come back to this slide. But we have add as this double nested lambda abstraction. We say we want to evaluate add 2742. The first thing that happens is that the 27 gets passed into the outer lambda. So then we bind x to 27. We have lambda y, 27 plus y applied to 42. And we can still reduce because we have a function next to something. We have a function application. And so we put 42 into the y, we get 69. But add 27 already is a valid function. So when you do map of add 27 on 1, 2, 3, you get a value. Now currying is available in most languages. It's the default in Haskell and ML, so you don't really even have to think about it. The only reason I'm presenting it is so that it doesn't confuse you when you see partial functions being passed around. When you see forms like this add 27, because that's fairly common to use partial function application. So for example, let me actually pull up just to show what I'm talking about. You'll often see people do, let's say that we have an add. Let's do something more exciting, multiply. X, y equal x times y. And you'll often see people do map mul 6 as opposed to a more cumbersome formulation here. So when you see it, I want you to know what it is. But you can define functions and use them without knowing how currying works. It's just much easier to read the code and understand the code if you do. And if you're not getting it now, like I said, it takes a while. Come to me. I'll explain everything. And yeah. So currying is the default in this language, but it can be done in others. So this is how Clojure would do it. And the left associativity of function application. Remember that function application and the function types are completely different things. The function application's left associativity is explicit in Clojure because in Clojure, the curried add takes one argument, and returns another function that takes exactly one argument. This is Scala. Now, Scala doesn't generally use currying. They generally put all the parameters on one parameter list, but you can curry in Scala. And this is what it looks like. And in the case of Scala, they make the right associativity of the arrow type explicit. This is what it looks like in Ruby. Curried add is a proc that takes an x, returns another proc that takes a y, and returns x plus y. Same theme, and you use .call twice, and you get your answer. And this is Python 2.7. I think Python 3 is probably the same. I just didn't check. And that's that. And one final thing that I'll talk about, because I want you all to go exploring with GHCi. I want you to look at the slides, try to find something that I'm wrong about. I don't think your odds are very good, but give it a shot. Strings are just a list of char. And a list is just a linked list, which I'll cover that in the next class. So all the list methods work on strings. Length is not a string method, it's a list method, but it still works. Same with map. You can do a 2-upper and you get the uppercase version. Now you might ask, isn't that really inefficient to represent a string as a list of chars? And the answer is yes. So Haskell actually has a type called text, which is what you would use for high performance string manipulation. But for the stuff we're doing, where your strings are going to be small, just use the built-in one. It works fine, and all the list methods are going to work. So
There's some sort of library we need to include to get the 2-upper method.
yes, data.char. I'll show you. So it's just import data.char, and then you now have 2-upper. Omar is the name of one of my cats. So. I'll also show you while we're here. Let's say that you do want to import data.text for some reason. That actually is going to make your life difficult because data.text also has a map function. So what you want to do is import qualified, like so, and then you don't have the namespace collision problem. So many of these libraries are explicitly designed not to be imported into the namespace, into the main namespace, but to be imported qualified. And you'll see some of that when we start looking at real code, which is going to be July 6th. Although I'm going to send that lab out a few days before. And now we're at cats. So that means if you have any questions, go for it.
Like cats in that 2-minute break.
Well, this time cat means 47-hour break.
Cat is not a stateless function.
It's because cats are objects.
Cats are objects.
You can't rely on them to always return the same thing.
Cats are people, damn it. They're not objects.
My cats have some really weird hash code behavior, I'm telling you.
Are there ways to inspect libraries like data.char? Can I list what methods can be called or what methods
Yes. That is browse. So data.char will give you all of the data.char.
What was that about?
Yeah, :browse.
Those are like special keywords specifically to GHCi.
Yes.
You can also do :help, right? Show all.
I'm not sure. There's another one. So obviously type is good for getting the types of things. There's the type of your plus function.
Can you move it up a little bit so it's like higher?
Oh, sure. Yeah, there we go.
Cool. Thank you.
And the other thing is sometimes you'll want to, so I haven't gotten into infix, which is like order of operations, like how it parses, the fact that times has to bind tighter than plus, that stuff. But to get the infix and the associativity, you can use info. That'll also tell you if you do info on a type class, it'll tell you all the instances that it knows about and all of the members that the type class has.
Where do you keep the body of a function?
The body of a function, no, because the body of function may not exist at compile time. You can look at the source on, this is, there are multiple, this is probably not very readable, but, so there's a thing called Hoogle, as in Haskell Google, that has all the haddock implementation. So like if you want to look at the source for map, and then look at the source, and there it is. There's also FP Complete has a more comprehensive Hoogle that just has more stuff in it. So,
Actually, I'll lead into my next question.
which is
Where you can suggest we go for the API.
Hackage. Yeah, Hackage is what it's called. And honestly, documentation is one of those areas for improvement in the Haskell world. It's getting better. It's getting a lot better.
That's Google package.
Yeah.
Okay.
Yeah.
So this includes, does package include like the Prelude stuff as well?
Yes. Yes. Prelude is just another module. It's just a module that is imported implicitly, unless you tell the runtime not to, or the compiler not to. Rob, what's up?
You know who's like decorators?
Decorators.
Maybe this is like a later class, but I'm just wondering like, if you want to take a function and transform it into another function, like, do you have to do that at compile time? Is there a way to, like, let's say you want to, like, add a database caching layer.
Sure. So one way to solve that problem, so you want to write a function and then you want something that you can put around that function to add database caching. One way would be template Haskell, which is what YSO does. And template Haskell is, it's for those who know Clojure's macros or list macros, template Haskell is the macro system. And it works. It's a little hairy, but it works. Do I have any questions from California? I don't know if you guys are still. Did they voluntarily go away, or did we lose them? Okay, that's good. That's good.
So, how do you, is it considered, like I know we're talking about we want functions that are sort of like stateless, right? Unless they specify that they're going to use some sort of state. I guess specifically I/O. My question is for, say you have something that's sort of like a Python generator or something along the lines that, say you just wanted to, the most simple is just a range function, right? So that like every time you say .call or .next or whatever, it's going to give you 1 to 100. Like, is it okay? Like, if functions occasionally won't exist at compile time or however that optimization happens, is it okay to like retain some sort of state in a function? Or how would you handle that? Sort of
Okay,
something that is inherently stable?
so there are two questions there. By the way, I have to go probably 7:20. I have a dinner at 7:30. Okay, so the first question is how do you do a generator? And the second question is it okay to have a function that has some kind of internal state that's not visible to the outside world? So the answer to the second is yes, and that's the kind of thing that unsafe perform IO is used for. What you use unsafe perform IO for is when the type signature has an IO in it, but you know for sure that it's actually referentially transparent. And if you know what you're doing, it's okay. If you don't know what you're doing, it's a disaster. As for generators, the list type in Haskell is actually lazy. So, for example, you can have an infinite collection. And then you can say, okay, I want to take 100 of those values, but I don't want to read the whole thing. Oh, I worked my GHCi by importing the data text, so let me redo this.
So you really, you provide a function that's a transformation from one to the next. Would be how you could sort of generate it.
Okay, yes, so for example, if you, like let's say that, so we have this val, which is just the integers, and then you could say like squares equal map square, then you can take 100 from squares, and it'll generate the squares. That's the sort of thing that, like that's how you would build generators. We also do have list comprehensions in Haskell. So if you want to do like x squared, or I think it's like this. That also works. And that'll come into play when we.
So can you do like x drawn from the integers and then like another condition? So
I'm
that's-
sorry.
Can you do like multiple conditions, like draw from the integers and then the size?
Sure. I mean, so like you can have guards, for example. That didn't work,
Well, so it'd be x squared less than.
of course.
And does it compute x squared twice here, or
Probably. I mean, written that way, it probably does.
Would you use a let in to stop that from happening? Could you use like a let in across the bounds and guards with a
Well, you can generate a list on top of another list,
Yeah.
and they're both basically evaluated.
What you could do
List.
is this guy. Do a filter on top of a map.
Notice that syntax doesn't have explicit like placeholder bars, like the less than 5,000.
Mhm.
Cover the line without, or is that just like a?
That's something I didn't cover.
Okay, cool. I'm just curious.
So yeah.
What about current?
Oh yeah, so it's sort of. Like,
Well, but this is-
implicitly curring.
But this is infix, so it's actually
if you leave out the 100, actually prints out the first 5,000, but it never stops because it keeps going on, I guess. So like it prints them out,
oh yeah, this would
because if you can't figure out statically like whether or not this terminates. So
yeah, this would not terminate.
Like it doesn't know that this sequence doesn't stop. But I guess that's like.
It just hangs, yeah, because everything else fails.
But can you like,
Oh,
can you
so
like
that's-
assign it and take from it?
I mean, yeah, you could do. Well, actually, that
Well, you can't